Hello everyone! In this episode I will implement rate limiting using Golang, specifically token bucket and sliding window algorithms, and then we will plug it into REST API as HTTP middleware. Let's get started! So, I'll start by converting the existing sliding window code into a reusable piece so we can use it in our middleware function. Specifically, the code in article is LeetCode style because the timestamps and IP addresses are given as input, and this is not the case in a real-world scenario where we have requests come in and we don't know how many of them we'll have. So we need to handle them as they come. So from this code, only this piece of code is needed for us to create a structure, and that structure will be created per IP of the client. So let's get started. For that, I'll create a new package called limiter and sliding window. In the package limiter called limiter, I'll create a struct called sliding window limiter. Right? And in order to later, I'm planning to create another type of limiter, which is token based. So I want to create a generic interface for both called RateLimiter and specific implementations of them. Like they both will implement RateLimiter interface. So in order to make sure, I will just point to the sliding window. I'll cast it to null. Okay, here I'll just return true. And as I said, I'll just copy this piece of code from here and paste it here. So first things first, what are the things that are constant here? Limit and time window, because they are given as info here. So we will just create a field inside the sliding window struct. I'll call it window, which is going to be integer, let it be larger, and the limit is going to be integer. Okay, let's create a constructor function that will return pointed to sliding window, and which will receive window as, and the limit as integer. Then we just set the struct field to them. Like this. Okay, so limit is going to be like, instead of s, I prefer calling it this. So here I will be this dot limit. And for lock, because I want to keep the timestamps they arrived, I will create like logs, which will be basically a queue data structure, and queue data structures can be implemented with list in Golang. Basically, this data structure is deck, which allows us to push back, push front, and their corresponding pop operations in constant time. So here, just use it as queue, okay? And I want to make sure we initialize it when we create new sliding window object. List can list has new method, which will return pointer to newly created list, and that will be enough for us. So basically, the idea of sliding window is calculate the edge time, then check whether the elements inside the logs are before that time. If they are, we just remove them. Otherwise, we break and check how many of them. And if we are within the limit, we can accept it. Otherwise, we'll deny it. So, yep, let's get started. So now let me get current time first of all. Then here I don't want to store them as integers. Instead, I will store them as time.time data structure, which is easier to work with times. So it's going to be this data structure. And here I need to get that edge time, which is calculated by delta. I'll call it delta. And now I need to convert it to Unix, so I get the seconds, and minus this window, right? And this is the delta in seconds. And now I want to create edge time out of it. For that, I'll just use time Unix operation and pass the delta, which is seconds, right? And the second argument is nanoseconds, so I'll just pass 0 there. Now we have edge time, and now I want to make sure, I want to check whether this element is happened before edge time, right? This element happened before edge time. So in Go, time structure has before before edge time, yeah. But before doing that, let's convert this requests. Instead of request, I'll go with lock, right? And now before should be working, right? Yeah, it's working. And here we check that each element happened before this edge time. If it is, we remove it. Otherwise, we break out the loop and go again. Looks okay. Push back now. Turn true. Otherwise, false. So basically, that's it, I think. We converted this code into a reusable piece. We accumulated inside this structure. And this structure, the instance of this structure, should be there for each client IP. And each client IP will have its own story of logs and logic. Okay. And now let's create a simple REST API. We'll create multiplexer first. New mux serve mux, okay. And this mux has handle function with root. And this is basically a really basic endpoint, which will write like hello there, okay. So set content type to application JSON, and we just write to it like a bunch of slice of bytes, like hi there, and that's it. And we'll just listen and serve it, address with multiplexer, right? Address will be, I think this will do. And listen serve returns an error. And in case of error, just log fatal, just log it and exit. We'll log it and exit. So now I want to integrate my rate limiting logic as middleware. So I want to guard this and other endpoints. For that, I just go and create middleware function called RateLimiter middleware, which will take HTTP handler as next, and RateLimiter, which is coming from, and this will return HTTP handler, okay, and HTTP handler function, and here we need to first get the IP of a client, then rate limit, then based on the result of rate limiting, we call next middleware in the chain. So first thing, we need to get the IP from the request. I want to create new separate function for that called get client IP, which will return string from request. I think net package has split function, which will basically split the network and port part of the client. And so if client is like this, it will basically split it with this delimiter and return them both. Like it will return host and port. So host, port, we don't need port. Error. Just check error. For now, let's just log it and return host, okay? Okay, now I just call that function with the request. Okay, we have the IP address of the client, and now we have a rate limiter, but each rate limiter exists for each client or each IP. So for that, let's create a map of IPs to limiters. Okay, IP limiter map is map to rate limiter. Okay, and IP limiter and exists coming from IP limiter map. If it doesn't exist, IP limiter is going to be rate limiter that we're receiving here, or accepting here. Then that IP limiter has allow method, and if it's not allowing us, then we just end it there with a status code. With the status code HTTP too many requests. I think it is right header. Right header. Status code too many requests. And we'll end it here. Otherwise, we just serve it. Okay, and now let's integrate it. And I want to create new handler, rate limiter, and pass it the multiplexer, and limiter, new sliding window. So sliding window, first one is the window for the past like 10 seconds. Limit, let's say 1 second, limit 2 requests. So 2 requests per 1 second, per second. And we just, instead of mux, we'll pass the new handler, which will wrap the existing multiplexer with this logic. And that's pretty much it for now. And I have a client, which client snippet, which makes HTTP request to this address and just prints the result status code. And before doing the next one, it sleeps for 100 milliseconds. So we can simply start the server, I guess. Yeah, it is started. And go run client. Okay. Here it comes. So client is making 50 requests. This is IP address. And what is being returned, we're logging. So remember the rate limiter is now set to, this is a window, time window, it's 1 second, window in seconds, right? Window, and the second limit, how many requests is allowed during this window. So in 1 second, 2 requests allowed. So the moment we started, 2 of the requests are used and they're both allowed. And further requests are denied until 1 second passes and another 2 requests are allowed. Okay, and the thing repeats here. So we can filter with grep where we have like 200 and log only that. See, request 1, 15, 14, 15, 34, 35. Yeah, only these requests are allowed. And we can even count them as word count utility function. Yeah, on 6. But in this approach, I see like downsides of it, limitations, because the request can be concurrent and parallel, the access to this map is not safe currently. So we need to kind of make it thread safe. For that, I can create like mutex from sync package. And before like accessing it, we'll just lock it. Then after that, unlock it. That will solve the problem, yeah. And I think there are another option we can use. Sync has its own map, I guess. Map, yeah. And why don't we just use that one instead of locking and unlocking manually? We can, okay, we can access it. It has, I think it has a load and store method. It will give the key. If it has the key, it returns the value. If it doesn't, it stores a new one. So we'll just pass the rate limiter here. And what is returned is a rate limiter. Then I think second one is loaded. We don't need that one. And now we just need to typecast it to rate limiter. And I think that's it. It should work the same. Let's check just in case. It should give us the same result. 6, yeah, that is working. So that was the implementation of sliding window algorithm, rate limiting algorithm, and we made it like reusable code. The next one is I want to show token bucket. Token bucket is another most popular rate limiting algorithm out there. And the way it works, you can like, briefly I can tell you, like there are tokens available and each request decrements that token number. And if there are no tokens left, a request is denied. And the tokens are generated at a fixed rate. For example, two tokens per second or something like that. And yeah, request can only be made if there are enough tokens. This is often used. Yeah, the advantage of using token bucket is that it supports bursts of requests. So as long as we have enough number of tokens, we don't care how fast the requests come. They can come all at once and drain the bucket of tokens. So it allows bursts of requests. But overall, it still constrains the number of requests. Okay. I'm sure there are pretty good resources you can learn more about token bucket algorithm. But let's create it. Let's create it. Token bucket limiter. So I'll just copy this code from here, and I'll call it token bucket limiter. Okay. Implement it now. So the way it works, as I said, we have number of tokens. We have tokens here. We have tokens. Let's make it. Let's make UN64, and they're generated fixed rate. So we have kind of fill rate, which I'm going to make it float. And we have, of course, capacity maximum. We should not exceed this capacity. And we have like last time we refilled the token bucket. Again, it's going to be time data structure. So the algorithm goes like, first we need to calculate how many tokens were generated since the last time. And that is calculated by multiplying the time passed from the last time, since the last time, multiplied to fill rate. Time passed since the last time in seconds multiplied to fill rate. And that should be added to our tokens. But with the capacity in mind. If it exceeds the capacity, the token number should be the maximum of capacity. Okay. So first things first, let's get the current time now. Then we need to calculate time passed. And we can calculate that now, subtract t.last time, right? And seconds. It will return the seconds duration, the floating point. This many seconds has passed since the last time. And now to add is going to be time passed multiplied to fill rate, right? And I want to cast it to unsigned 64. If to add is greater than 0, it means we need to refill the bucket with this much of tokens. As I said, we need to make sure we need to make sure the capacity. So minimum of these two, okay? T.tokens plus to add this much. After that, we update last time to current time. And after this, we check that if tokens available, if I have enough tokens to serve our request, we decrement the token count and return true. Otherwise, false. Okay. This is basically it. I guess. And we implemented this interface. Everything is ready here. All we need to do is just switch these two. I'll just copy this for now. Limiter, a new sliding window. Oh, we didn't create the constructor function for token bucket. Let's create it. Function new token bucket limiter returns token bucket limiter. And this will accept like rate in float 64 and burst in I guess integer. Okay, burst is going to be integer 64. Okay. Tokens is burst number, fill rate is R, and capacity is B. Last time is time.now. That's it. And now we have token bucket. We have to give the rate limit, like 2 requests per second are being generated, and the burst will be 10. Burst will be 10. Let's see how it behaves. We'll start the backend, and for now let's check it out with this. Okay, as you see, okay, good. As you saw it, that first 12 requests were almost at the same time, right? But they were allowed. That's of what token buffet varies from the sliding window. It allows bursts of requests. Like we had 10 requests and 10 tokens, and the 10 requests were drained all of the available, and while they were using them, 1 second passed and new token, like 2 tokens per second, were generated. So in overall, it is 12 tokens used. Then he started denying further requests. Next accessed, like 2 second passed, like half a second passed, then 1 generated, half a second passed, and the second one generated, like this. Yeah, we can count it with this one. How many requests out of 50 were actually allowed? 19. Okay. Suppose let's increment the number of tokens generated per second. Let's make it 2.3 tokens generated per second. So this number should increase because more tokens are generated. Well, because it is like small number, the difference will be like if you make it 3, I guess. Oh, we did not restart the main server. I'm changing it and not okay. Let's make it 2.4 first. Restart the main server. It is. I'm restarting the client now. 2.4 should give us better result. No, it did not give. Okay, let's make it 3. Check with 3. Yeah, it's 22. more requests allowed. So I think, yeah, this is reusable piece of code, middleware. We are using sync.Map to provide concurrency of code, but we did not actually check concurrency here, because to the same IP, two concurrent requests can arrive at the same time as well. So we need to guard it as well. Like, I will create mutex. Okay, here. Mutex is going to be mutex. And now I'll just t.mutex.lock and defer t.mutex unlock. Like this, okay? And the same, by the way, goes to here. Mutex, sync.Mutex. And in here, this mutex unlock and defer this mutex unlock. Yeah. Everything should work now. Good. Now our code is concurrent save. Did I miss anything? I think no. Is it production ready? Well. I think I would give much concern and work on it. But if you want to use similar RateLimiter, I'm sure there are already libraries and packages available for production use. But here you'll get the idea of how to implement a RateLimiter like this. Actually, when you use like one of the popular RateLimiter algorithms out there, packages, it's called Rate from the Go's external packages. And if you just swap this RateLimiter with the one from the external library, you get the same result with these same values. Yeah, you get the same result, the same number of allowed requests with the same accepted arguments. Okay. So, thanks for watching and happy coding.